Morning, everyone. Before we get started, any question? All right, so we will take a look at the Excel project number 5 first. And after that, we will do some lecture on chapter 9 and also some other contents, right? So first of all, let's go back to the Brightspace. And also I posted this bonus project, as I mentioned in the class. So if you guys want to get some extra credit, right? This extra credit project. It's worth 10 points plus the midterm exam. And then if you click on it, there's extra credit. This is the actual project, right? Our project. It's not too many problems. It's just 1, 2, 3, 4 questions. Right? So then just basically using all those R codes, right, to analyze the data sets called empty class. It's very popular data set in the RStudio. Okay, and also I put a sample sample code. Right, this is I create this using R Markdown. And you can use it as a reference. Right, go over this. It should give you now need the coding parts. Also give you some kind of like refreshment on this how to code and how to analyze. Also provide comments on each kind of like each graphs, so you can use that to work on your bonus extra credit projects. Right. Now it's going to be, let me just put on the due date, right? Again, it's due on 19th, on the last day of the semester, 19th. All right. You can just upload it here, right? Upload a file here, and then I'll grade it and then get back to you. Okay. So that's a extra credit project.
Thank you.
Sure, yeah, okay. Next thing, let's take a look at our project number 5. So here, let's go back to Excel demo one more time, and let's click on the lab 5 practice. It's about a hypothesis test, right? So basically just perform a hypothesis test for 3 different scenarios, for the z-test, the t-test, and then for proportion, set population proportion and population mean. Okay. So let's download this file. Okay, let's open the file. I'm going to share the screen with you in a second. Okay, go. Yeah, so this is our Excel project number 5. Now let's go through this project together. So enable editing. So find test statistics, critical z-scores, and then come up with the conclusions here. That's our first part. So first of all, we will calculate test statistics. So this is about population mean. The first one is about population mean. We have X bar here, mu, sigma, and sample size. Alpha is given here as well. The second one is a t-test, right? Also t-test for the population mean. And the last one is the z-test for the population proportion p. Okay, so let's get to it. First of all, we'll take a look at question part 1. So here we'll do this. So open parentheses, and then we do X bar, which is C5 minus D5 over open parentheses, population standard deviation by square root of the sample size, which is 50. Okay, now we close parentheses. That's give us the test statistics. And then we can also use this, since we use the cell operations, and we can mimic those 2 formulas to get the other 2 test statistics. And next thing is find out a critical z-score here. So this is a right tail test, right? See, right tail test, alpha is 0.05. So the critical z-score is located on the right tail. So and the area to the left will be 1 minus 0.05. So we do non-dot IMV, right? Inverse of the normal distribution, or actually non-dot S, IMV. Inverse of the standard normal distribution. And then probability here is area to the left, so it will be 0.95. And you can just do 1 minus 0.05, equally good. When he enter, we'll get the critical z-score. It's a 1.645. And also we can find the p-values, right? P-value using the test statistics. And right here, UB, this test statistics is located in the right tail, 2.95. But we want an area on the right tail, so it will be 1 minus non S BIST. And we're using this test statistics H5 and accumulating everything to the left. And that will give us the p-value on the right tail. Here you go. Now again, the p-value is so much smaller compared to alpha, right? That means reject HO. So that's a first question. Any comment or anything you're not following? Okay, and then let's look at the part 2. So on part 2, we already calculated test statistics. Now we need to find out a critical z-score. Now this time is a left tail test. You see left tail. So the critical z-score is located on the left tail. So we do this. So now that's the IMV. And open parentheses. And probability, because the left tail, so alpha is concentrated on the left tail, so 0.1. And that should give us the critical z-score here. Okay, now we hit enter. That is minus 1.28. Okay. And let's calculate the p-value, right? So p-value is using this, right? This test statistics to find the p-value. So this one will be lambda S BIST, and then using z-score, accumulating everything to the left, true statement. Then he enter, we will get the p-value, which is almost 0, right? You can expand it a little bit more decimal. You'll see that it's close to, it's very, very small, but almost like 0. And again, this is because of z-score is so small, right? This means it's a 6.32 standard deviation below the mean. And this is very, very extreme, right? That's why we get a reject HO. So same thing, right? Reject HO. Okay. Any question about this? Okay. The third one is two-tail test. So we already have test statistics. Now let's find out a critical z-score, right? So there are 2 critical z-scores. I'm going to put one underneath it. Okay, so let me just format the painter here. We're gonna need one on the left, one on the right. Okay, we're just gonna put it right below it. So here, the one on the left tail, lambda S T, no, not inverse, not inverse. This is inverse of the standard normal distribution. So the probability on On the left tail will be 0.01 by 2. And that will give us critical z-score, right, on the left tail. On the right tail, it's going to be none dot s dot iv, and then it will be 1 minus 0.01 over 2. And that's the critical z-score on right tail. You know, if you enter, we get that. It should be exactly the opposite, right? If you don't get it exact opposite, that means your work is off. So you need to go back, double check. Now let's find out the p values based on the test statistics. So now this one is, first of all, we need to find out the area on the right tail because test statistics is positive, right? Now one thing is that the test statistics is between these two numbers. So that falls within non-rejection region. So that means we fail to reject HO. Okay, that's based on the critical value method, but based on the p-value method, this is going to be, we're going to double the area on the right tail, right? And the right area on the right tail is 1 minus lambda s dot dist. And then we're using this test statistics and then comma true. Okay. So remember to double the area because it's two-tail test. Two-tail, we get a double the area on the right tail. Now if you enter, we get the p-values. And as you can see, this p-value is so much bigger compared to alpha. And the last one, we failed to reject the HO. So that's going to be the part one. Any question about part one? All right, let's look at part two then. Second part on the t-test. And there's a right tail and a two tail. So first of all, we put equal sign, open parentheses, sample mean minus population mean by open parentheses, sample standard deviation over square root of the sample size. So that will render the test statistics. So you get that, 3 decimal, and then just drag it out. Get a test statistics for the part, for the second part. Now we need to find out a critical t-score, right? So it's on the right tail, that means alpha is concentrated on the right tail. So here the critical t-score will be t inverse. And then probability is it's going to be 0.95, 0.99, right? It's 1 minus 0.01. That's everything to the left. And the degree of freedom will be 30 minus 1, which is 29. The sample size 30 minus 1. That's going to be the degree of freedom. And then once you hit enter, you get that. So the critical t-score is going to be this. And also we need to find out the p-values. So you do this. And so the p-value is based on the test statistics. And then we are looking at area on the right tail. So it's 1 minus s dot dst. And then we're going to take this test statistics. And then we are accumulating everything to the left. Okay. Yeah, let's do it. And then once you hit enter, you should get p-values. So again, this p-value is very, very small because this test statistic is so large. It's 4.642 standard deviation above the mean. So again, compare the p-value to alpha, and then we see that it's less than alpha, so reject HO. All right, and then let's look at any question about this. And the second part is two-tailed test. Okay, so we start with the critical t-scores, and then alpha is 0.05. So again, we also need two values, right? So one on the left tail, one on the right tail. So we do this t dot inverse. And on the left tail is 0.05 or 2. Right, so the alpha is pretty evenly on both tails, on both left and right tails. Degree of freedom is 12 minus 1. And then it will give us the critical t-score on the left tail. On the right tail, very similar t dot inverse. And it's going to be 1 minus 0.05 by 2, right? That's the area on the right tail. 1 minus that, that's accumulated area to the left. And degree of freedom is still 12 minus 1, 11. And we get the same thing, right? Same result, opposite result, right? That's what we expect. Now, let's look at the p-values. So again, this is two tail. So we need to double the area on the right tail. So here is going to be first equal sign to double the area. Area on the right tail will be 1 minus area to the left. So now S dot vi is t, or parentheses, put a test statistics, accumulate everything to the left. And once you do that, make sure to double the area. It's very important. Double the area on the right tail. Key enter, you get this, and this p-value is much bigger than alpha. Okay. That means you failed to reject the HO. Also, if you look at the test statistics between those two, right? Those two critical values, that means test statistics fall in the non-rejection region. So fail to reject HO. Yeah, same conclusion. All right, and then the third one is the z-test about the population proportion P. We have a P values here, and then we also need to know Q. Right? So you do 1 minus P. And we'll get all the Q values. That's out. I'll make this. So calculate those one first. And then after that, calculate the test statistics. So it'll be P hat minus P over square root of PQ, P times Q over sample size. And then that should give us the test statistics z-score. Yep, so if you enter, we should get a result. Okay, that's a typo here. Okay, let's see. Yep, accept this. Okay, so it's 0.48, right? Let me see. Yeah, C5 square root. Yep, no problem. It's all good. All right, hit enter. Now we can get the rest of the work now. Again, we only need 2 decimal places, so let's just okay, just keep it as 2 decimal place. Now next thing we will take a look at the critical z-scores. So on the two tails, That's I will insert one below here, insert no, below it. Okay, now we're going to need one here, right? So which is because there's a two tails, so we're going to have a left tail and a right tail. So now let's first of all find out the critical z-score on the left tail. So it'll be s dot IMV. Now we divided alpha by 2, get the area on the left tail. So it's going to be 0.05 by 2. That's the critical z-score on the left tail. Again, I'm going to just turn it into 2 decimal place. And also on the right tail, s dot IMV. And the probability will be 1 minus 0.05 by 2. And then key enter, you get this 1.96. Again, the test that this is fall within these two critical values, critical z-scores. So that means fail to reject it show, but we can double check with the p-values. The p-value based on that. Because the two tails, so again, we're going to double the area on the right tail. So 2 times area on the right tail is 1 minus area on the left. Now s dot dxt open parentheses, take the z-score 0.48 and then accumulate everything to the left. That should do it. So we expect the large p-values, right? Because the test statistic is so small. This is very large, actually, 0.6312, right? That's a very large number. So conclusion is fail to reject HO. Any question about this? Now let's take a look at the R2, right? Left tail test. So again, critical z-scores. And this time only have its left tail, so the critical z-score is located on the left tail. You just do this. Now s IMV, and then we can just directly take this number, right? G19, or you can just type in 0.01. Either way you like. And close parentheses. That should give us the critical z-score. So that turned out to be minus 2.33. And this number is bigger than that. So it doesn't fall in the rejection region. So our conclusion should be fail to reject. But we can double check. One more time, double check with p-values. So we do lambda s dot dst. And this z-score is on the left-hand side, left tail. So now we're accumulating everything to the left. And we should the enter, we got this, right? It's 0.0654. Yeah. And this is much bigger, right? This is bigger than alpha. So again, so the rejected control. All right, and then part 3, third part. Okay. Now again, we'll take a look at the critical z-score first. And then this is right tail test. So this alpha is fully concentrated on the right tail. So we're going to do the lambda s dot IMV, and then we are using area to the left, which is 1 minus 0.1. And that will give us the critical z-score on the right tail. Yeah, 1.28. So and then we can calculate the p-values using this is right tail. So we do 1 minus area to the left, dot s dot st, and then take the test statistics. We are accumulating everything to the left. And key enter, we will get a p-value. Let me see, maybe too many decimal. It is. All right, and then again, this p-value is much bigger than the alpha. But again, failed to reject the HO. So that's going to be the demo on the Excel project number 5. So now I'm going to give you 25 to 30 minutes. I guess maybe you can finish in 30 minutes because it's I'm going to save this file. I'm going to upload it. Solution. You can use it as a reference, and then you can, meanwhile, you can go back to the Brightspace and then click on the actual project number 5, right? So I'm gonna upload this to our Brightspace course. And once you finish this, and then we're gonna start a lecture on chapter 9 on the chi-square test. So let's go back to Brightspace and let me upload this solution file. So lab 5, project solution. We'll change the current file. All right, so yeah, so I'll put you in a breakout room, right, for like 30 minutes, and you guys can finish the Excel project number 5. And if you have any question about the Excel project or anything about our course, feel free to talk to me. All right, so your actual project is this, right? This one is also due on August 19th, but it's better you just knock it out. Let's look at it together. Excel project number 5, updated. All right, so now if you don't have no question, I'm gonna put you in a breakout room for like 30 minutes, and then we'll resume in 30 minutes. Okay.
If we have questions, do we stay in here
Oh
or
no, you stay in the breakout room so I can talk to you on an individual basis.
okay.
Help you on an individual basis. All right, guys, let's resume. Okay, so we're gonna go over the chapter 9 lecture. So let's you guys can open the PowerPoint as well from the Brightspace course. Okay, so let's take a look at that. It's called a chi-square test. So basically, it's a statistical analysis and a hypothesis testing combination, kind of like a test. So you take a look at the hypothesis. So this is a typical hypothesis test. So we basically perform that two type of test. Test for independence, test of independence. And also test of goodness of fit. So we take a look at both in a second. Okay, so what is a chi-square test? This is the test examine the observed frequency and then expected frequency, right? Difference between those two. So there are two types of tests, which goodness of fit and also independence test. And the formula we are using is just this, right? Chi-square equal to chi-square value equal total of observed frequency minus expected frequency squared over expected frequency. And we work with several examples, right, from real world. And also we'll take a look at the critical value table. So that's a table called chi-square table. I'm going to show you how to use that in a bit. And also there's a kind of like a post-assessment, right? Like after run a test, we can take this Kramer's v-test to see how strong is the association, the strength of the correlation or like association between those two variables. And we take a look at some pitfalls and also and we'll see some comparison between the chi-square test and other tests. And also distinguish when not to use the chi-square test. So let's run through the details. So first of all, chi-square test is non-parametric statistical test that measures how well the observed categorical data or like observed frequencies matches with the expected frequencies. It's named after the Greek letter chi, so it's called chi-square. And produces the test statistics that follow a chi-square distribution, and chi-square distribution look like this, with very long right tail, something like that. So it's kind of like a very skewed to the right test. It's a very skewed. Right. This is what chi-square look like, and then we basically figure out a critical chi-square, right? Critical chi-square on a table. And it's not like a critical z-score, critical t-score. We also have similar nature like that. So it's chi-square critical. And then alpha is concentrated on this right table here. So it's a lot like z-test or t-test. And this test is mainly used for non-parent. It's mainly used for those nominal and ordinal data. Meaning, most of the time we deal with the categorical data. Although it has a kind of like a measurement within each category, but it's still, you know, on a broader sense, we work with the nominal or ordinal categorical data. Then it's a non-parametric test of the count data, meaning frequencies, right? Count data is kind of like frequencies. That's why we can also say expected frequency and then observed frequencies. So, and then here normality is not required when we run the chi-square test. That's why even with a very small sample, this test works well. And we have two goals. One of them is a test for independence. Second one is a test for goodness of fit. So two basic tests. All right, so let's look at the goodness of fit test. So we basically just test if one categorical variable matches the expected distribution. So for example, like if you're rolling a dice 60 times, is head or tail equally likely, right? Those are the kind of like set up for the goodness fit test. And then also like a broad type, right? Distribution, does it match with the national data? Does the blood type distribution match national data? Website visit, equal across all 7 days, right? Meaning if there's a variation among all 7 days, then that means observed is not equal to expected. So if they are equal, then observed equal to expected. So this is the idea of the test for the goodness of fit. Also, we have a test of independence. So after binary, so basically we have a different outcomes, right? Row variable and a column variable, categorical variable. So they have different layers. I want to test if the row variable and then column variable are independent from each other. So the second test is test for the dependence. So you look at two categorical variables, if they are associated or independent. Okay. So one of the example could be like, is gender related to study method preferences? Let's say people prefer face-to-face or online or like hybrid, all those different like teaching mode. Okay. And then also, does the smoking affect the disease diagnosis? Right. That's another. It's in the medical field. And then also another example could be, is political affiliation linked to the income bracket? So for the test of independence, the HO is always row variable. Usually we just call row variable and a column variable. See, they are independent. And then also for the goodness of fit test, the HO, so H1 here must be row variables and column variables are associated. So variables are associated, meaning they are not independent, right? They're dependent. You can also say they are dependent. Variables are dependent. And for goodness of fit test, then observed equal to expected, right? Observed distribution equal to expected distribution. If that's the case, then it's a good fit, right? Meaning this data set, it's a good fit. Now let's look at the formulas. So the formula is very simple, right? So we got chi-square, and then this is summation sign. So here, this means sigma is a sum up all the square term, which is, this is observed frequency. This E means expected frequency. And so O means observed, E means expected. Now we just basically calculate the chi-square values, and then we compare that with the critical chi-square values, right, from the chi-square table. You'll see that table in a bit. So the step one, we state a hypothesis. Now is variables are independent. H1 is variables are associated. Then we basically collect and tabulate data, meaning building the continuity table with observed frequencies columns. And after that, we calculate the expected frequencies. Expected frequencies calculated using row total over column total by the grand total. And you can also say grand total as a sample size. It's equal sample size. And after that, we calculate the chi-square statistics. So chi-square is the sum of the observed frequency minus expected frequency, parentheses square, divided by expected frequencies. Now we'll sum up all cells, right? And then find the degree of freedom. And then degree of freedom for the test for the independence is going to be number of rows minus 1 times number of columns minus 1. For goodness free will be degree of freedom is k minus 1. And let's take a look at example, right? Test for the independence. It's about gender and also the preferred study method. So we have two genders, male, female. And this is the observed frequencies, meaning this is what you get out of your sample. So you split it as three different. So there's a column variables. It's a visual, auditory, and readings. Three different categories, three different layers. And row variable has two layers. It's either male or female. And as you can see, this here sample size. This is sample size 150. So basically, we pick 150 adults, right? Adult learners, and then we come up with this kind of like a tally, tabulate to the data set, get this. And so also there's a row total, right? Like the total male will be 70, right? This is total male. Total female will be 80. And then total visual learners, visual study methods is 50 people. Total auditory study method will be 45. And then also total reading method learners, that's going to be 55. Yes, Caleb.
Just to double check, when we get to the expected frequencies where it says row times column divided by the by n, where are you getting row and column from again?
Okay, it's a row total. It's actually it's a row total and a column total.
Got it. Thank you.
So basically, for the first one, so for this 30, right? So this is the expected frequency. So we need to do the calculation on this part. So we are taking this 70 times 50 and then divide by 70 times 50 divided by 150. And that turned out to be 23.3. Row total, column total, divided by grand total, which is sample size. And for female, it's going to be 80 times, 50, right? Over 150. So we get 26.7. So 80 by 3, that's 26.7. And previous one is a 70 by 3, so it's 23.3. And then for male under the auditory column right here, this one, it's going to be 70 times 45 divided by 150. 70 times 45 over 150. When you simplify, you get 70 times 0.3, so that's 21. And then next one is a female in the auditory group. So we do row total 80 times column total 45. So 80 times 45 over 150. And then if you multiply that, simplify, we get 0.3 times 80, that's 24. And then for the reading of the female and the reading category, that would be 70 times 55 over 150. We do the calculation, it will be 25.7. And that will be last one. It's the expected frequency for female falling under reading study method. It's going to be 80 times 55 over 150. And that turned out to be 29.3. Right? So then basically we do the formula chi-square. Formula is sum of the sum of observed frequency minus expected frequency square over expected frequency. So the first one will be observed frequency 30 minus 23.3. Square that divided by 23.3. And the second one will be 15 minus 21. Square that and divide by 21. And the third one is 25 minus 25.7. Square that, divide by 25.7. And then this one will be 26.7. I mean, be 20 minus 26.7. Square that over 26.7. And then second to the last will be 30 minus 24. Square that over 24. The last one is 30 minus 29.3. Square that over 29.3. So now here we calculate the chi-square, right? We add up all those values, get chi-square 6.78. So this is test statistics. And degree of freedom is 2, so will be number of rows, right? We have 2 rows, 2 minus 1, times number of columns, 3 columns, 3 minus 1. So this is 1 times 2. That turned out to be 2. And then the critical, we're using alpha equal 0.05. So the critical chi-square value will be 5.99. Let me show you how to get that. I'm going to keep this. Let's go back to Brightspace. And then let's go back to chapter 9. No, actually, under the syllabus and formula sheet, right? Should be under the syllabus and formula sheet. Here. Now, go down here and open the chi-square table right here. And download the table. And once you download the table, you'll see this chi-square table. So right here, so degree of freedom in our case is 2. Alpha, you see, this is alpha, 0.05. They have intercept, and intercept is 5.99. Okay, this is how you find out the critical chi-square values. Okay. Any question about this? The freedom together with alpha, right? So 2 common alphas, 0.05 or 0.01. And let's go back here. Now, here, once we have this, we decide on the critical chi-square values, 5.99. Now we draw this chi-square test. I'm going to use different color. So this is chi-square critical value. So alpha is 0.05. So that we found the table is 5.99. And then the value we have is, so this is rejection region, right? The tail on the right tail is rejection region. So that means our test statistics is 6.87. 6.87 is right here. And that actually fall in the rejection region. Okay, so we get a reject nature. That means they are associated, right? Meaning gender and then preferred study methods associated. They have impact on each other. They are not independent. Okay. Any question about this? It's a lot like what we did so far about the hypothesis test. It's just different type of the hypothesis test. Now let's take a look at this, right? Another goodness. So this one is a goodness of fit test. Okay. It's about MMM color distributions. Those are sweet, sweet stuff, right? So let's see. So we have Mars claims that M&Ms follow the color distribution. Red is 13%, orange is 20%, yellow 14%, green 16%, blue 24%, and brown for 13%. And this is expected frequency, right? This is expected percentage of frequency. So let me just so expected frequency is given. Supposed to be based on that claim. And now here, and we look at this is the observed frequencies, right? So this one here. Out of 200 MMs that sampled, there are 24 red, 38 orange, yellow is 31, green 28, blue 52, and then brown 27. So if you look at, so this is observed frequencies, and the expected frequency is 13%, 20, 14, 16, 24, 13, right? So you do 200 times 13%, get expected frequency of 26. And then 200 times 20% will get 40, right? Expected frequency of 40. And then 20%, 200 times 14%. So the expected frequency is going to be 28. Now 200 times 16%, and that turned out to be 32. And then 200 times 24, that's going to be 48. And then after that, 200 times 13%, that's going to be 26. You get all the expected frequencies, right? Again, we're using this observed frequency minus expected frequency squared over expected frequency. And then here we are testing for the goodness of fit, right? Meaning HO here is expected distribution equals to observed frequency distribution to observe. And then H1 is not equal to each other, not equal to expected, not equal to observed. And so this is how now I know to hypothesis. Now the observed frequency, so the first calculation is going to be 24 minus 26 over 26. Running to do that in place, it's 0.15. And the second one is going to be 38 minus 40, square that, and divide by 40. And the third one, so this turned out to be 0.1. This one is the exact values. And then the third one is 31 minus 28 square that over 28. And once we do the calculation, it's approximately equal to 0.32. And next one will be 28 minus 32 square that over 32. And that's actually 4 square, 16 over 32. That's exactly 0.5. Next will be 52 minus 48 square that. You get 16 over 48. That's 1 over 3, right? 1 over 3, 1/3 is 0.33, approximately. And the last calculation is going to be 27 minus 26 square that over 26. So it's 1 square over 26. So 1 over 26 approximately equal to 0.04. And then we're going to sum up all these numbers. And it turned out to be chi-square is 1.44. So this is test statistics. chi-square. Then the degree freedom is a K, meaning number of the layers here, right? K is a number of layers, a number of categorical, number of categories, right? I can say number of categories. So here you see there are 6 colors, so you do 6 minus 1, that's 5. And then alpha is 0.05. So now you go back one more time, let's go back to the table, chi-square table. So it's 5, and then alpha is 0.05, and then intercept is 11.007. So that's basically the chi-square critical value of the chi-square value. Critical value. So we get the critical value 11.07. Now go back to the so we get this. So this chi-square, so if you draw the curve, this critical chi-square value here, it's 11.07. Right. And the test is based on this alpha here. And this is rejection region. This is non-rejection region. And then test statistics actually falling in the non-rejection region here. It actually goes here. And then this in the non-rejection region, that's why we fail to reject the chunk. So that means your MMM back does not significantly differ, right? Meaning observed expected frequency and observed frequency are consistent, meaning they do not differ from the claim distribution. Meaning the retailer is honest about the outputs of their product. Any question about this? So this one, it's goodness of fit test. If you look at goodness of fit, it's only one variable, right? One categorical variable with the different layers and the goodness of fit test. For the independence, as for independence, we have row variable and then column variable. They both categorical variables. So that's the main difference between these two tests. All right. Now let's look at another example, right? So this is still testing about independence. So we have a smoking status and a heart disease. So we have basically survey 500 patients. And we try to figure out if smoking habits associated with a heart disease diagnosis. Okay. So basically, this is all the observed frequencies, right, from the survey, right? This is observed frequencies. And then the first expected frequencies, right? So this is all income. So the first smoker under the with a heart disease is 250 times 150 divided by 500. When simplify, we get 75, right? So the expected frequency here is 75. And for this second category, smokers with no heart disease, we do 250 times 350 divided by 500. When we reduce it, it's 175. So expected frequency here is 175. And then the expected frequency for the third one, which is non-smoker heart disease, we do 250 times 150 divided by 500. And that turned out to be 75. So again, this is 75. And then the last category, which is non-smoker with no heart disease, is going to be 250 times 350 over 500. So 250, and when you simplify that, right, you get 175 as well. So the expected frequency is also 175. So we get all those observed and expected frequencies. Now let's do the calculation. So 90 minus 75, square that over 75. And then 160 minus 175 square over 175. And 60 minus 75 square over 75, we get this. And then last one is 190 minus 175 square over 175. We try to combine them, we get pi square 8.57. And our degree of freedom here is number of rows, right? Number of rows, it's 2 rows minus 1. Number of columns, 2 columns minus 1. So this is 1 times 1 as well. So degree of freedom is 1. And alpha, again, it's 0.05. Usually people just use 0.05, 0.01. And then again, go back to the table, chi-square table. You see 1, and critical chi-square value is 3.84. So that's what we got, 3.84. And then again, the chi-square actually, it's falling in the rejection region because chi-square critical, it's just 3.84. And then the test statistics, actually, it's 8.57. So actually, it's the rejection region. And then this value here for in the rejection region. And that means we're going to reject HO. So reject HO here. So that's basically reject HO, meaning HO is they are independent. Reject HO meaning they are associated, meaning in other words, saying this is smoking status have impact on the heart disease. They are associated. The conclusion is that smoking status and heart disease are associated. It's another test for the independence. Any question about this?
Yeah, I have a question. So, do we need a table to find the p-value over there as well?
P-value is not needed. So the p-value is only used in the test for the goodness of fit. So let's go back a little bit, right? So in goodness of fit test, we only test one categorical variable. In this case, it's color of the M&Ms. So there are 6 colors. There's no, it's only row variables, no column variables. Make sense? And this one has usually appear in a percentage, right? It's called a expected frequency, percentage of frequencies.
Oh, no, I'm talking about like, so you know how we have like both the critical value test and the p-value test? So for this example, you
Oh
can
yeah,
see on the bottom, they give a p-value. Is that found in a table?
no, the table wouldn't give that. But don't worry, right? I'm going to show you how to get it in Excel. I see what I mean. Okay, so I'm going to share the screen with you. So you can look it up in Excel. So it's called a chi-square inverse. A p-value, so it's a chi-square distribution. Chi-square DIST. And then you're going to put in and we want an area on the right tail, right? So it'd be 1 minus area to the left. So 1 minus chi-square distribution. Let's go back to see which. So here the test is 8.57. Okay, so I'm using 8.57 there. in Excel. Degree of freedom is just 1. Right? In this case, we are accumulating everything to the left. That should give us the p-values, right? 0.003. Yeah, so that's actually, we can also look up the critical value of the chi-square, right? In this case, we can double check. So we do chi-square dot inverse. And you're going to put a probability values, which area to the left is going to be 1 minus 0.05. Degree of freedom 1. Yeah, and give us this, right? 3.84. That's exactly what you see from the PowerPoint 3.84. Right? If you want more decimal, like more accuracy, use Excel. But that's basically how you find out the p-value. So then, no, there's no table for that. It's just too many items. If people try to come up with a table, it would be too many items, too many probability values. So it's inconvenient.
Okay, makes sense.
Yeah.
Thank you.
Sure. Yeah. So this is another example for example 4. So again, this is another test for the independence. Maybe tech company surveys 300. So it's app ratings for each group. Tech company surveys 300 users about the app satisfactions, satisfy, neutral, and dissatisfied. So again, we can only test for the independence, right? That's the only thing we can do. That's for independence because of we have a row variable and then column variables. So test for independence. So now, so the total people they survey 300, right? And matches with those users. Once we have a row total and a column total combined, we should expect to have that. And then for the first item here, the expected frequency is calculated using 100 times 180 by 300. 100 times 180 by 300. To simplify, we get exactly 60. And the second one will be, this is actually 100 plus 80. So 180 over 300. So 8,000 by 300 turn out to be 26.7. And this one is going to be 100 times 40 over 300. So 13.3. It's 4,000 by 300. So 13.3. And then this one will be 100 times 180. 300 as well. It turned out to be 18,000 by 360. Then the middle one, it's 100 times 80 by 300. And divide into that 26.7, and second to the last one on the second row, 100 times 40 by 300, 13.3. And then last row, first one is 100 times 180, same thing, right? Over 300, still going to be 60. And this is 100 times 80 by 300, still going to be 26.7. Last one is the same, 140 by 300, 13.3. And now once we have this is our observed minus expected, square that over expected, and we're going to come up with a chi-square of 8.33. And then here the degree of freedom is 3 rows, 3 columns, 3 minus 1 times 3 minus 1. So 2 by 2, 4. And then alpha is 0.05. We go back to table, chi-square table. So degree of freedom 4, right? And then alpha 0.05, 9.49. That's exactly what we see. 9.49. So again, it's a equal to the chi-square distribution. This is a rejection region here on the right tail. Chi-square critical is 9.49. And test that this actually is on the left hand side. Yeah. So this is non-rejection region. Again, we failed to reject control. That means app ratings are independent of the age groups. Okay. So meaning they are independent of each other. The company S app is equally well received across age groups. So independent. No significant relationship between age group and app satisfactions at alpha equal 0.05. If you want to find out the p-value and then the other one, we can use the Excel one more time. So the p-value here will be 1 minus chi-square st, and our test statistics is 8.33. Degree of freedom 4, relative true. Now 1 minus that's area on the right here. So the p-value is 0.08. Again, it's greater than alpha. So same thing, right? Failed to reject HO. And also the critical chi-square inverse. Avidity value it's 0.95. It's 1 minus 0.05. Degree of freedom it's 4. You see 9.49. When you run through decimal place, 9.49. So yeah, so basically we can double check, right, using the Excel. Yeah, so that's another test, right? Test of independence app ratings by age groups. And then our alpha just give you some, common values right here, but we already have it. Right? We can look it up on the table. It's easier that way. And also, effect size is called a Cramer's lead test. Basically, if you want to see if the significant chi-square tells us if the association exists, right? Meaning if the test is significant, then we still need to see how strong it is. So we can use this formula called V value based on Cramer's V equals square root of open parenthesis chi-square divided by n times k minus 1. K is the smaller of the rows or columns. N is total sample size. So that this is the benchmark, right? Negligible, small, medium, and large. It depends on the V values. The V between 0.00 and 0.10 with a little or no practical association. The 0.1 to 0.3, that would be weak but detectable association. And if it is 0.3 to 0.5, then it's moderate, meaningful. And from 0.5 to 1, then it's going to be very strong, practically significant. So if you look at the gender study method test, right? You do go back a little bit. Gender study, this one. So chi-square is 6.87, and then N is 150, and K we're going to use 2 because row has only 2 layers. Using the smaller one, so that's why you see this. Yeah, k minus 1, right? 2. You're using 2. 2 minus 1 give us 1. So it'll be 6.87 over 150 times 1. And that turned out to be 0.214. And this fall in this range. So it's a small to medium effect. We can try another one, right? Try the one we just did, like this one. So this one, row and the column are the same. So here the n is 300, so we need n 300, we need it. And then the k is 3. And the chi-square is 8.33. So going back here, using this test, the square root of 8.33 over 300 times 2. That's going to be square root of 8.33, 600. And when we divide that, see what that is, right? We will put it to the Excel. Square root 335,600. And this turned out to be 0.117. Again, that's a weak, but the detectable. So 0.1178. 0.11. And that fall in the small, weak, but the detectable association. All right. So that's basically the Reimers retest. So again, as assumptions and then common pitfalls. So basically, categorical data are required, right? When we run the chi-square test. And then we have two types of tests, independence of observations. Each participant contribute to exactly one cell, no repeated measures, meaning we take a unique measures. Repetitive measures is not preferred. No, we don't want the repetitive measures. And also expected frequency must be greater than 5. If not, then we're going to merge categories or use Fisher's exact test. If it's too small, meaning there's a bias. Usually, bias. If there's a bias, then it's not reliable. The result is not reliable. Also use a raw count, not percentage. Input the exact frequency. We don't usually use percentage or proportion because due to rounding. The rounding may lose accuracy, but exact counting frequencies is better. And also the association is not causation, right? It's not causal relationship. We do not infer the causal relationship. Basically, it's a to a certain degree, right? Maybe it's a small association or medium or like large, right? Or like negligible association, depends on different cases. And also the test is very sensitive sample size. Very large sample can produce significant chi-square even for trivial associations. Right? So in this case, this indicates they prefer a smaller sample. Right? Larger the sample will like dilute the final result, right? Dilute the significant chi-square values, make it inflated. Okay, so that's why it's not good. Yeah. So that's basically a common pitfalls to avoid. This is just something we learned, right? The last two we didn't learn. That's okay. We learned the chi-square test, t-test, right? And then we have ANOVA test, correlation, right? That's where you just, if you review the chapter 10 and chapter 11 videos, you know correlation is basically relationship, linear relationship between two variables. So so if this decision rule is if there's categorical data, we usually go with the chi-square test, right? If we do comparing means, then we do t-test or ANOVA test. And then if we want to examine the relationship between the two variables in terms of strength and direction, we use the correlation. That's just some kind of like a different sets of rules for different tests. Yeah, so again, that's just a decision-making step, right? So if p-value less than 0.05, reject HO. It's using p-value method, but you can only use p-value method using Excel. Right? And also, if the p-value is greater or equal to 0.05, then fail to reject HO. Just like any hypothesis test, same idea. So that's a lot of real-world applications, right? Healthcare, education, marketing, political science, biology, business, psychology, sports science, and sociology. Any field we can name it, right? You can run those tests, especially chi-square test. It's pretty handy and a useful test. So any question about this? Chi-square test? All right. I guess maybe let's take a 15 minutes break. And we come back and then we can go over chapter 9, right? Briefly go over chapter 9. But you guys, if you reviewed, how many of you guys already reviewed a video? How do you feel about a video? Does that help you understand the correlation, regression? Anybody want to share the thought?
I thought chapter 10 was pretty easy to understand, but
Mhm.
I think chapter 11 maybe had some extra
Okay,
things that I might want to review more of.
sure, sure. I'll do that, right? So I will, chapter 10, yeah, I feel that. I feel, yeah, same way. Yeah, chapter 10 is pretty straightforward. So I'm gonna, when we come back from the break, I will go over the chapter 11. Okay, so on the simple linear regression, I will go into those difficult parts of the simple linear regression, especially the outputs, like analyzing the outputs. So yeah, so that's
Wait, actually, don't we also need to cover ANOVA for chapter 9?
yes, ANOVA, yeah. Let me see, right? I think so, yeah. So that maybe let me cover ANOVA first. So I'll often come back. ANOVA is mainly computed using Excel, but it's okay. I'll show you how to get Excel outputs. You know, in terms of detailed calculation, people usually don't do that. Um, so we're gonna take a look at ANOVA, yeah, when we come back from the short break. Okay, sure. All right. So we will resume in 15 minutes. Okay. Yeah. Thanks, Austin. Thanks for the reminders. I paused recording for a second, so forget to reopen it. So one more time, let's go back. Okay, so we compare means with identical natures, right? That's what we're doing in a one-way ANOVA. And then we will understand different analysis variance designs. So you can actually design this in your own study. We're also going to evaluate the assumptions of the model, ANOVA model, and then perform this single factor ANOVA is also called one-way ANOVA. And there's a Tukey test, which is a post-analysis. There's also you can identify which two population means are different, right? Which two means are different using the Tukey test as a post-analysis. Okay, so then let's see. Let's get to the. So basically, there are usually one variables, right? It's called a column variable with different layers, right? Or different factors, right? Factor on the treatment group, treatment variables. We usually just look at the one independent variable, but it's categorical, have two or more factors. And then one factor contains 3 more levels, and the other factor may contain 2 or more levels. And then the plan used to testing analysis. So it's a hypothesis test. Again, it's a hypothesis test. It's like chapter 8, right? Just another type of hypothesis test. And then also called a one-way ANOVA, also known as one-way ANOVA. In experimental units, subjects are assigned randomly to treatments. Subjects are not assumed homogeneous, meaning they are unique. Subjects are unique. Homogeneous means unique. And then only one factor or independent variables with 3 or more treatment levels, right? Now we would call this analysis of the one-way ANOVA. Okay. Let's look at this.
Sorry, Professor.
Sure. Yeah.
Doesn't homogeneous or homogeneous mean not unique? Like the subjects are not unique, but the treatments are different?
Oh yes, subjects are identical, but the treatments, yeah, are unique. That's right. Subjects should be right. That's right. Yeah, that's a mistake. Yeah, subjects are identical, homogeneous, like similar in nature. Probably better, similar in nature. But experiment groups are different. That's right. But that will be unique, right? Unique experimental groups. All right. So now let's look at this. Evaluate the difference among the means of 3 or more groups. That could be the accident rates for first, second, third shift. Right? Like expected mileage for 5 brands of tires. So 5 unique brands, right? And then, but the tires probably perform a similar nature, right? Have a similar function. Okay. So the assumption here is the population are normally distributed. And the population have equal variance. Normal distribution should be implied, right? Population of equal variance means sigma 1 square equals sigma 2 square equals sigma 3 square. If assuming we can write as many as we want, sigma 8 square. And as samples are simple random sample, right? Or like randomly or independently drawn, meaning simple random sample. It's the best. Now this hypothesis test, right, for one factor ANOVA, which is HO, is all population means are equal, meaning mu1 equal mu2 equal mu3 all the way to mu-n, right, or mu-c. And so that's and the null hypothesis. And the alternate hypothesis, not all of the population means are the same, meaning at least one population mean is different. Let's say And then if we want to figure out the post analysis using two-key test, then we can actually identify which two population mean are different. Okay. That's a way to do that. We'll get to that in a second. But yes, so that's basically our most important hypothesis test, right? And then we are using F-test. F-test is what we use. We'll take a look at that in a second. And so HO, H1, and then all means are the same. If the null hypothesis is true, right? If it's not, then at least one of them is different, meaning that they have the same normal distribution, right? The all means are the same. And then it could be some of them are the same, right? Like a mu1 equal mu2, but not equal to mu3. Then mu3 is totally different from mu1 and mu2. Right? Population number 3 is different, totally different from population number 1 or population number 2. And then maybe all of them are different, right? Mu1 is not equal to mu2, not equal to mu3. So all of these are possible, especially when we have a more population means and we have more kind of like distributions, right? Or like combinations, possible arrangements. Yeah. So now this is ANOVA table, right? So in our ANOVA table, there's a between groups. So basically, between groups meaning if let's say 3 shift, so the C will be 3. Or like in this case, it will be for 5 brands, then C will be 5, right? That's between groups. And then also there's a within group. So the degree freedom for between groups is C minus 1. So for that shift example will be 3 minus 1, 2. And then within group will be the sample size minus number of the categorical variables here. And if you combine these two, this total degree of freedom is n minus 1. Right? That's always the case, right? In the sample, the degree of freedom is always n minus 1. And we're going to have a sum of the square amount. We're going to calculate sum of the square amount and sum of the square within. And then you divide sum of the square amount by degree of freedom, you get a mean of square amount. This means mean square among different groups. And then sum of the square within over degree of freedom for within the groups, and we get a mean of square within. And then once we do that, we do F value is a mean of square amount over mean of square within, right? The quotient of those two. And basically, we find out the F value. F value gives us the P value. So that's basically the mechanics, right, behind the one-way ANOVA table. But we also see that from the chapter 11 and 12. So that's something, you know, we go about. So here, one factor ANOVA test. So HO, H1, that's the null and alternate hypothesis. And then we use an F value, which is mean of square amount over mean of square within. And then MS amount is mean of square amount variance. Amount meaning among different categories, right? Categorical variables. And the mean of square within is within the entire sample, right? That's why it's a sample size. Degree of freedom 2 is a sample size minus number of the categorical variables. And degree of freedom 1 is associated with a mean of square amount. That's a number column, number groups minus 1, right? Or number of categorical variables over 1, minus 1. And the F test, again, it's a lot like the chi-square test, right? It's a skew to the right test. And then again, we put alpha, which are critical values on the right tail. And then that will give us F values. So alpha and then degree of freedom, DF1 and DF2, right? We'll have intercept. So let me quickly show you what F table look like. Let's go back to the bar space. We need to go to check them out. No, go back to the syllabus and the formula sheet. Now you're gonna see there's F table down below. So this is called F table. Download the table. Once you download the table, it looks like this, right? So DF1, degree of freedom 1 goes on top, and this is only this table only apply to alpha equal 0.05. And degree of freedom 2 goes to the here, right? And they have intercept. And then this 2, intercept is the critical F values we're looking for. Just like critical chi-square values, right? Very similar nature. Now let's go back to PowerPoint. Yeah. So DF1, DF2, and then together with the alpha, we get the critical F values, right? And then we're gonna have a test that these F values. And so if test that this F value is greater than critical F values, then reject H1. But if the test that this F value is less than critical F values, then fail to reject H1. So this is again two type of decision, just like the other hypothesis test. And this is another, and then let's look at the concrete example, right? You want to see if the 3 different golf clubs yield different distances, right? So you randomly select 5 measurements from trials on automatic driving machines for each club at 0.05. That's alpha. Alpha is 0.05. Is that a difference in average driving distance? Average driving distance for 3 different clubs. So so basically we do this, right? We calculated the mean for sample mean, right? For first club. So add up those 5 numbers, divide by 5, we get this. And then the second club, we do the same. Add up those 5 numbers, divide by 5, we get this. And then add up those 5 numbers, divide by 5, we get this. And then the average of those 3 clubs, driving distance for those 3 clubs, you sum up those 3, divide by 3, we get 227, right? So basically, we will try to see, where this the relative standing of those 3 population means using this using a comparison of the sample means. It looks like this one is way ahead, right? First club, second club, third club. Once we put it on the graph, we see that pretty clearly. And then we want to see if this is actually true for the entire population. So we're gonna run the ANOVA single factor, and then we basically can get this, right? Let me quickly show you to get ANOVA outputs. We'll go back to this. I'm gonna take all this and then paste into the Excel. Oh, I can see that. Oh, yeah, that's good. I'm just gonna label this, that's all. So this is club 1. This is club 2. And club 3. Let's just format this really quickly. So that I get the data entry here. So next one, just label that property. Now we just highlight this and then go to data analysis. And we're gonna see ANOVA single factor input range. Well, this will be this. Just the numbers. Okay. And then no labels in the first row. Actually, you know what? I want labels. So I'm gonna reselect this, including labels. So labels in the first row. Now output's gonna pick a alpha equal 0.05, right? Output range, I'm just gonna pick a cell right next to it. And I'm gonna show the results. And then this is gonna be the ANOVA outputs. Right? Like the average, you see the average, we calculate that. 226, 205.8, and the variance. And that's a summary statistics. Basically you have a count 5, right, for each category, for each categorical variable, club 1, club 2, club 3. So that's basically how we get ANOVA outputs. And then right here, that's among groups, and then degree of freedom, sum the square between groups, right? And sum the square within groups. I'm just putting all this here. So sum the square between groups is 4716.4, and then divide by degree of freedom. So we have 3 different clubs. So degree of freedom DF1 is 3 minus 1 is 2. And divide this number by 2, you get 2358.2. That's a mean of square between groups or among groups, among 3 groups, 3 clubs. And then sum the square within 1119.6, and then dividing by degree of freedom 12. That comes from the sample size, which is 5 by 3, 15, minus 3 columns, right? N minus C. So it's 15 minus 3. So that turned out to be 12. Now we divide the sum of the square within groups by degree of freedom, we get 93.3. Then you do mean of square among groups over mean of square within groups, and then we get F values. And then F value will give us P values. And then the critical F value, we can look it up from table, is 212, right? 0.05. So if you go back to the table, it will be 2 and then 12, right? You see 3.89 right here. Okay, 2 and 12. And also we can just use the Excel to do this. All right, we can verify these critical F values using, it's called a F. In this case will be F inverse. Okay. So the probability values, so probability value is 0.05. So then 0.05, no, actually it's 1 minus 0.05. That's area to the left. And the degree of freedom 1 is 2. Degree of freedom 2, DF2, degree of freedom number 2 will be 12. And you see we get this 3.89. Right? You run into do that more place. And the p-value associated with this, we can also verify that it's going to be F distribution. And then X value is this, F values, degree of freedom. And we want an area on the right tail, so it must be 1 minus this F distribution, put in the F test statistics F values. Degree of freedom 1 is 2, degree of freedom 2 is 12. And we are accumulating everything to the left. And as you can see, you get something, you get the exact match, right? P values. So that's basically how we get ANOVA outputs, right? From Excel. And it's very straightforward. You can easily get that. And you will be given this, right? Even if it is on a final, you'll be given. Okay, so you don't worry about this. You just need to focus on analyzing the outputs, right? Interpreting. All right, so that's basically what you see from here, right? That we just run through that one more time. And then we get this F values, P values, and then since F value is much bigger than, right, so based on this distribution, because of the critical F values, this is a rejection region, right? So the F test, this is for in the rejection region, right? So reject HO. So that means at least one population mean is different, right? Among all three clouds. That's our conclusion, right? So you look at the p-value so small, less than alpha, so reject HO, meaning there's a sufficient evidence that at least one population mean differs from the rest, right? So we basically successfully complete the hypothesis test for one-way ANOVA, one-factor ANOVA. And then the follow-up, which is called a Tukey-Kramer procedure, it basically tells us which population mean are significantly different. So like the one we just did, right? We know at least one of them is different, but we don't know which two are different. Then we can perform the Tukey-Kramer test. After we reject the null hypothesis, right? If they all equal, then no Tukey-Kramer test needed. Only if at least one population mean is different, then we can perform the Tukey test. I mean, Tukey test allows pairwise comparison. You take two population mean at a time and then compare them, yeah, with a critical range. So then this is how we decide a critical range. So we're going to need a Q table, QU. So using the Q table, mean of square within from the ANOVA outputs, NJ will be number of items in one of the categorical variable, like club 1, 5, right? In the previous example, that NJ is 5. NJ prime will be in group J prime, right? It's also 5 because they are equivalent, right? So we have identical amount of the same amount of the driving distance among three clubs. So NJ is 5, NJ prime is 5, right? In that example. And then QU, it's a value from with a C and n minus C degree of freedom. So C is number of the categorical variable, right? Layers of the category. So 3 layers, club 1, club 2, club 3. So C equals 3 in that example. N minus C will be 15 minus 3, 12. So N minus C is 12. So 3, 12. And that will give us and Tukey-Kramer alpha is 0.05, right? So using the Q table, let me show you how to look up in the Q table for the QU, right? Critical standardized range distribution value. Let's go to, it's right here. This is a Q table. Okay. So C, right? This is C, and then this is the N minus C. Okay. So C in our example will be 2, right? And then N minus C is 12. So they have intercept. So this turn out to be, you see, bold phase type is the is for alpha equal 0.05, and then 0.01, and then light phase is alpha of 0.05, and in that example is 3.08, right? So this QU in that example will be 3.08, 2 and 12 have intercept, right? No, 3 and 12, my bad, it's 3 and 12. So that should be 312, that's 3.77, right? That's a QU. 3, 12, alpha 0.05. Let me just download this and upload it to our Brightspace course. You can use it as a reference. Okay, let me just upload it to the Brightspace. Yeah, so last one is the Q table. Okay. So now let's go back to the PowerPoint. Now we get to nail down all those values, right, from the table V2. So now in this example, you see QU is 3.77. And then we compare this, right? We do the sample for the first club, sample mean for the first club minus sample mean for the second club. The difference is 23.2. And the sample mean for the first club, sample mean for the third club is 43.4. And then sample mean for the second club, sample mean for the third club, the difference is 20.2. And then based on the Q table, C equal 3, N minus C equal 12, we get a QU is 3.77. So going back to this, to previous slide, right, this will be 3.77 times square root of MS reading is this, 93.3. Take that number, 93.3 over 2 times 1/5 plus 1/5. So that's going to be 2/5, right? And the simplify will be, so basically this is how you calculate critical range for that. So this turned out to be 16.285. So again, NJ and NJ prime it's like a sub-sample, right? It's sample for each category. Right? For club 1, the sample is 5. For club 2, 5. Club 3 is 5. So NJ means for club 1, and then NJ prime means for club 3. Right? Just pick 2 random categories in your categorical variable. And we'll calculate this, and we get 16.285, and then it looks like you see all these absolute difference are bigger than the critical range. That means they're all different, right? Meaning population mean for club 1, and then population mean for club 2, and population mean for club 3. They are totally different at a 5% significance level with a 95% confidence. So that's basically, this is how we perform a Tukey test. This is called post-analysis, meaning after we reject the HO, then we can perform the Tukey test. Right, so I think that should be, actually there's a 2-factor analysis variance. Maybe we can run through that, but it's very similar to the one we just did, right? 2-factor, just that's going to be row factor and a column factor, right? So this is called a 2-factor ANOVA. So we examine the effect of 2-factor interest on the dependent variables, and then like percent carbonations and line speed are soft drink bottling process, right? If they have kind of like interaction between those two. And an interaction between the different levels of these 2 factors. That's the effect of one particular carbonation level depends on which level of the line speed is set. That's the interaction. We try to nail down if there's interaction effect for the 2-factor ANOVA. So assumption is the same as a 1-factor ANOVA. Populations are normally distributed and populations have equal variance. And then we have a simple random sample being selected, right, from the population. And then, so here it's a little bit more complicated, 2-factor ANOVA. So we have an I is the number of the levels of factor A, so A and B. C is the number of levels for factor B, right? And then N prime is the number of the replications for each cell. Okay, meaning, and let me give you an example. Right here, right, replications will be in each cell. So we have 5 different boxes, right? 3 machines, and then 5 different boxes. So replication will be 2, right? Each replication will be 2. Will be each machine and then the corresponding box. So that's n prime, right? Number of replications for each cell. N is the total number of observations in all cells, but that's going to be the sample size, right? The entire sample size. For this example here will be 2, will be, let's see, 2, 4, 6, 8, 10. 10 by 3, right? So it'll be 30. So sample size of 30. So it's look like it's 3 times 5 times 2, right? You can also calculate as 3 factor B, 3 levels, factor A, 5 levels, and then number of replications 2. That will get 30. And then total number of the observations in all cells. Talk about that. Nijk is the value of the kth observations in the level I of the factor A and the level J of the factor B. So 2 levels, right? I and J from 2 different factors. And here we get 2-factor ANOVA summary tables. This one is with replications. Could be without replication, meaning it's unique, but that's a very rare case. But usually it's with replications, make more sense. So the degree of freedom for the sample for factor A, right, would be number of rows minus 1, right? And then degree of freedom for factor B, for column, right? Column is factor B, and the rows are factor A, okay? And C minus 1. And then we get a sum of the square for factor A, right? SSA, sum of the squares for factor B. And then we're going to get a mean of square for factor A based on the sum of the square for factor A over degree of freedom for factor A. And the mean of square for factor B is sum of the square for factor B dividing by degree of freedom for factor B. Also, there's interaction. Right? Interaction between factor A and B. So you do R minus 1, number of the rows minus 1 times number of columns minus 1. We call this SSAB. It's the sum of the square for interaction between AB. Then so the mean square for interaction between AB is sum of the square for interaction between AB over degree of freedom. And we have this mean square, right? That's what we use. So the F statistics, so that performing 3 hypothesis tests. Test for the factor A, test for factor B, test for interaction. So that's why we have 3 F stats. So now also we have this within error, which is R times C. Degree of freedom is R times C times n prime minus 1. So n prime in that example is going to be 2, right? 2 minus 1. Rows, which is 5 rows, 3 columns times 2 minus 1. That gives us the degree of freedom for within errors. So the sum of square error dividing by degree of freedom, we get a mean of square error for within errors. And this is the base when we calculate the F stats. Right? So you do mean of square for factor A over mean of square for error for within errors. Then we get F values for factor A. And then mean of square for factor B over mean of square error. That gives us the F values for factor B. And then mean of square for those interactions. MSAB, mean of square for interaction of A and B over mean of square error. And that gives us the F value for the interaction factor. So then we perform 3 F tests, right? So like this is the example. So we got 3 filing machines, 5 different filing times, right? Box 1, box 2, box 3. If they have different average filing times when used with the 5 types of boxes. So 5 different boxes and 3 machines. And basically, we see if there's a difference in machines or in boxes, or is that an interaction between the machine and boxes? Maybe a particular combination performs the best, right? Have the best performance, or a typical combination have the worst performance. We can also look into that. So basically, we get this for that box example, right? We have factor A is the row factor. You see, we have 5 different boxes, right? So that's why it's a degree of freedom 5 minus 1. So it's, and the sum of the square for factor A is 7.4714. And divide this number by 7.4714 by 4, we get 1.8678. So that's the first one. And then for columns for machine, right? Factor B, this is factor B. This is factor A. Factor B, that's 3 machines, so 3 minus 1, degree of freedom is 2. And the sum of the square for factor B is 106.298. Divide that number by 2, we get a minus square for factor B. And then the interaction, we do number of rows, 5 minus 1, number of columns, 3 minus 1. So it's 4 times 2 is 8. That's a degree of freedom for interaction. Sum of the square for interaction is 9.7032, and then divide this number by 8, you get a 1.2129. That's the mean square for interaction. And then we do the within errors, right? So we do 5 times 3 rows times columns times n prime minus 1. Right? So rows is 5 rows, 3 columns, right? 3 machines, 5 boxes. And then within each subcategory, there are 2 items, 2 minus 1. So that's going to be 15, right? So degree of freedom for within error for error term is 15. And the sum of the square for error term is 7.5994. And divide this, and we get 0.5066. Now after that, we divide mean square for factor A by this, right? Now we get 3.6868. And then for factor B, dividing 53.149 by 0.5066, we get this number. And for interaction effect, you divide this number by 0.5066, and we get 2.3941. And that's the F values. Test statistical F values. And then with the given P values, right? Again, if the P value is greater than alpha, alpha is 0.05. Reject HO. If the P value is less than alpha, which is 0.05. Yeah, P value is greater than alpha is failed to reject. Failed to reject. And P value less than alpha reject. And so based on a P value, so this reject, reject, failed to reject. P value. So the factor A, meaning population mean, are different. So here means the average filing speed for those 5 boxes, since we reject HO, right? Meaning at least one of them have different filing speed. And then for factor B, same thing, right? For factor B, reject HO, this is highly significant, meaning the average filing speed for those 3 different machines are different. And so then fail to reject this, right? Meaning there's no interaction effect. So the hypothesis test, it should have a, let me see, there should be a slide with all the hypothesis test. here. It's here, right? Yeah. So the first hypothesis test is F test for factor A. If F value see mu1A equal mu2A equal mu3A, meaning for factor A, that's 5 boxes. So box A, box 1, box 2, box 3, they have a same average filing speed, right? And then each one is at least one of them different. Since we reject HO, meaning at least one box have different filing speed. At least one. Have different filing. And as for factor B, very similar. So 3 machines. So in this case, will be mu1B, 2B, 3B, right? That is 1M, 2M, 3M. Need to be so using box 1, B1, B2, B3, B4, B5. Okay. And that means again we rejected 12 because the p-value is so small. So at least one machine box, one machine has a different filing speed. So last one we failed to reject. The third test is test for the interaction effect. And since that F value, that because the p-value is larger than alpha, right? Alpha is 0.05. So fail to reject intro, meaning interaction of A and B equals 0. So that's basically all 3 F tests for 3 different factor A, factor B, and then interaction. And then we just basically analyze the ANOVA output, and we'll get a good idea about this. Right? So I think it should be sufficient for our course, in terms of analysis. There's a Tukey test, but you can also look it up using this, right? There's a Tukey test. You can also run a Tukey test, see which one, right? For factor A, factor B, different factors. We can look into either one of that, but it's okay. We're not going to go into details. So, any question before we end the section? So, on Monday, we will go over chapter 11 and 12. And if you guys want to review those videos, feel free to do that. Right? I also put the Excel demos, right, on those videos. Right? If you want to review those as well. Right? So and then that's pretty much for today, right? I'll see you guys Monday then.
See you Monday.
See you. Bye.
Thank you, Professor.
Thank you.
No problem.
Thank you,
Bye.
Professor.
Bye.